This week on FX Guide TV.
We attend the CVMP conference in London to look at the role of the GPU in VFX.
This and more coming up next.
Hello, I'm Angie and welcome to FX Guide TV. This week we're off to London. FX Guide is a media sponsor of the annual CVMP conference held each year in the UK. And as such, we are proud to be able to bring you some of the key presentations each year. But I'll let Mike explain further.
Thanks, Angie. For the fifth consecutive year, every film nominated for an Oscar for Best Visual Effects used NVIDIA technology. As Angie said, FX Guide partners with the CVMP conference in the UK. So for this week's show, we wanted to bring you Will Braithwaite's NVIDIA talk on GPUs in VFX. This is a great summary of the state of the art, and it's also a really good roadmap for the next couple of years. You'll hear at the end of this, he actually mentions the GTC conference, which is coming up. This is a GPU conference that's happening next month, and our own John Montgomery is going to be there. So keep an eye out on the site for special reports and some really important stuff from that annual conference. But now here is Will in London at CVMP.
All right, I'm going to try and make this not some kind of sales pitch, so you'll have to forgive the NVIDIA logo in the corner of everything. But obviously we have most of the information about our particular products and things like that, so I'll try and just miss off the NVIDIA bit and just talk about the concept of GPUs in general. I'm also going to apologize for the fact that, given that this is NVIDIA, I'm going to have to show a picture of a video game at some point, so I thought I'd get it out of the way really early on in the talk. This is interesting because this is actually when I got into graphics, 1985. This is my first foray into graphics, playing it, obviously. Meanwhile, other people with a lot more money were working with the first ever distributed memory parallel systems. That was exactly the same time, 1985. I don't think Leisure Suit Larry was designed to run on those systems. These days, we don't really refer to them as video games anymore. These days we think about them as interactive entertainment. And you can see 30 years, the graphics has come quite a long way, as we would expect. Now the reason for that is, of course, games are a simulation, if you will, of the part of the human experience. You're trying to capture part of the human experience. And a lot of that experience is a visual experience. So if you present something that doesn't look like reality to a game player, it's difficult for them to really get a handle and have an immersive experience that they want to achieve. So they need things like, globe illumination. They'll need photographic effects like deferred lighting and motion blur and depth of field. They'll want destructive environments, big simulations, pyroclastic clouds. They need liquid simulation. They want materials that are subsurface scattering and look very realistic. With displacements, and they'll want to do the whole thing in 3D, and they'll want to do the whole thing at 60 frames per second. So that's kind of what they need. Unfortunately, the movie industry does not make this any easier because we're always pushing the idea of what an acceptable reality is. We're giving people hyper-reality now in the movies. So you can be pretty sure that immediately after seeing this movie, the gamers all went out and started blogging about how they want to drive a giant Jaeger robot through an ocean, fighting with big, organic, translucent creatures, all at 60 frames per second in stereo. Science, on the other hand, has to deal with serious problems. Big planet-wide systems like computational finance, radio astronomy, protein folding, seismic exploration, the big issues that we have to deal with. And obviously climate modeling is a very large problem which needs quadrillions of calculations per second. So our billions really doesn't quite cut it. So you've got to think, why are video games still important then? I mean, we're so far behind what we really need to do. Perhaps there are other ways to do it. Perhaps we should be looking at other technologies. But video games are one of the fastest growing industries in the world. They're currently at nearly $80 billion. The movie industry, for those who don't know, is approximately $130 billion worldwide, including things like Bollywood and Nollywood and so forth. And video games are growing all the time. Video games, I keep saying video games, interactive entertainment is much easier to monetize as well. Because it's interactive, there are a lot more avenues of exploration for making money. So the return on investment in research is massive. So this is funding all the GPU development that you see. So I'm going to talk about how we went from a graphics coprocessor, because this is almost exactly 10 years ago. This is early 2003, PlayStation launch. I'm going to talk about how we went from that to completely generalized systems which are capable of sating the gamers' need for exceptional graphics, but at the same time running in the largest, in fact, an integral component of the largest supercomputers in the world. Now I'm going to start probably where most of your eyes have immediately been drawn to. 2003, the age of the semi-clad fairy. And this is a very important time, not just because of that. It's a very important time because this is when programmable shading suddenly became capable of containing relatively complex programs. Suddenly we had real branching, real conditional branches. We weren't doing everything with predicates anymore. We introduced render to texture, enabling us to have some kind of feedback loop, which opened the door to algorithms, possible algorithms such as partial differential equations and so forth. So this was a very important time. It was also around this time we were all at SIGGRAPH starting to see papers with the affix on the GPU. And we'd look at the paper, well, we'd look at the results first, and we'd go, well, those are very impressive results, and we'd read the paper, and we'd roll our eyes, and we'd go, oh my gosh, that is completely impractical. There is no way I'm going to try and convert my computational problem into a textured triangle at low precision. So we had a lot of work to do, but people kept doing it. And the reason why they kept doing it, and the reason why it was so important, was because, of course, we were in the era of parallelism. By 2003, we were well and truly in the era of parallelism. Frequency scaling was considered dead. We'd sort of hit this power wall, and 3 gigahertz was as fast as we could really get this thing to go. So if you wanted to go faster, you had to go wider. Another important note, looking at this slide again, is the order of magnitude of the transistor count was going up by 3, or more than 3. We went from 250 million transistors on a die to 7 billion in just 10 years. So obviously the nanometer process was getting so refined and transistors were becoming so small that this isn't something that we couldn't ignore this. So the idea of programming now was to work out how to get as wide as possible and still make yourself able to produce code in a decent amount of time, because of course the effort was going to go up. And this same thing happened with regular CPU cores as well. We saw a single core in a system become a multi-core system, amortizing the cost of the power and space requirements of a system. And then we saw the same thing happen actually on the core themselves, and they became vectorized, much like they did at Cray in the 70s. And these were really difficult to program and required intrinsics, and I stay very far away from things like SSE programming, because it just adds so much development time, it's not really worth it. The reason why we're doing this is because, like I said, we hit this power wall, but there's another power wall, a bigger power wall. The idea of if we ever want to reach exascale computing, we're currently at petascale computing, we need to be able to provide that much computational power. In other words, we need to have that many cores running. And if we just scaled this example here from 2011, which is roughly a 2 petaflop machine at 7 megawatts, we're going to get up to the power requirements of a large city. So currently that takes the power requirements of a small city. Presumably they've all left their lights on. It's an American city. So if you take the idea of vectorized instruction sets further and just go, I'm going to vectorize the entire machine, the entire device, you can get rid of the complicated intrinsics, and the whole thing becomes a scalar machine again. You can also play about with other optimizations to hide the latency, and you don't require large caches, you don't require branch prediction, and all the space on the die and the power requirements that takes up. A CPU will be about 50 times more power just to do all of that crazy branch prediction and scheduling. It's very clever, but this way you don't necessarily need it. And so you end up with a chip that looks a little different. It has most of its space taken up by transistors. And remember, those transistors are getting smaller all the time. Intel's currently leading the field with that, and they have the small, I think they're at 16 nanometers now, possibly less. So obviously, you're going to start seeing that exponential improvement in performance if you can use this architecture. And you start seeing that lovely Moore's law exponential curve that Andrew Davison showed us that I wouldn't dream of showing you, where Intel was very flat down at the bottom and NVIDIA was rocketing up into the heavens. Titan is the new version of Jaguar. This is at Oak Ridge National Laboratory. And Titan runs at 17 petaflops. That's not theoretical. Theoretical is about 30 petaflops. It actually runs at 17 petaflops with the Limpact tests and benchmarking tests, and it only uses 8 megawatts. That's 1 megawatt more for a 10-fold improvement by moving to this architecture. It has inside of it about 20,000 CPUs, each with 16 cores, and 20,000 GPUs, each with 2,700. That's 2,700 cores. And of course, this stuff is scalable. This stuff is scalable to tiny devices like cell phones or Roombas or fridges or cars, or it runs in your desktop, sating the gamers or us with our copy of Maya or Modo, and runs in the cloud. We have passive cool server configurations. So like I said, this stuff is great if you can use it. And that's the biggest problem. Of course, we work in a domain where we can absolutely use it. And image processing is a shoo-in for this kind of technology. That's why you see such great speed-ups there. But there are a few things we had to overcome in order to make it something that people would want to use. The first one was floating point. People used to say, well, that low precision isn't going to cut it at all. So over time, we gradually started making it capable of doing the kinds of things people who do climate modeling and other supercomputer-like things need to do. By now, we support everything. Full floating point. Don't let anyone tell you that a GPU isn't precise enough, because it absolutely is, including double precision, which only gets faster all the time. People didn't want to have to write everything in terms of a shader, so we give them a huge amount of languages to choose from, including some shader languages as well if they're stuck inside that kind of graphics pipeline. But you can write programs in C++ and MATLAB and Python. We give them an ecosystem of libraries you can just download and plug in immediately. You want to do FFT faster? Just plug in this library, and it happens to run it off on the GPU. And half of these things are free. Open source projects, huge community of those, including PCL, which have the open source implementation of the Connect Fusion that Andrew Davison showed you yesterday. There's stuff that's totally relevant to our industry, specific to our industry, like OpenSubdiv, all accelerated on GPUs, obviously. And there's more complex libraries that deal with the problems of significant problems that are going to really change the way that we do things like video games and how we visualize graphics in the future, like optics, our ray tracing engine. Of course, we didn't have a way of debugging. We couldn't do profiling, and we didn't have IDEs that really understood any of this stuff. Now we have all of that too. And you just download it and you just go. And if you're looking for people who actually know how to program a GPU, well, because it's so important to both supercomputing and video games, and hopefully by the end of this talk you'll see us as well, university courses have increased in tenfold, learning specifically the paradigms of GPU computing. Before it was just about philosophers eating spaghetti and sharing forks and things like that. Now it's all about prefix sums and radix sorts, and it's very different. So supercomputing 2012, those green blobs are all the ones using GPU computing. Whether it's AMD GPU computing or what Intel might be coming out with, or any of those things, these are doing GPU computing. So it's more than half of the whole. So this is pretty obvious. It accelerates HPC. I'll cut right to the chase and say how this can also accelerate visual effects. I'm also going to talk about some of the problems that we have and why it's kind of an issue that we need to solve. Issues that we need to solve in our architecture, in our, the way things work, so that it becomes a lot more accessible for people. Obviously, I showed you the image processing, so DI is a shoo-in for this stuff, and it's very difficult to find a DI system that isn't using GPU acceleration for grain reduction and color correction and so forth. So there's not much to talk about there. It's just so obvious. The same thing for editorial as well. I mean, people don't wait and people don't render out their sequences anymore. They just scrub right through and see everything that they're going to get. In fact, that interactive preview is the first thing that we saw, including what happens inside the DCC app, like Maya 2013 on the left there compared to Maya 2014 for television work, where the assets aren't using a crazy amount of volumetrics and really, really complicated materials. You can actually get pretty much a WYSIWYG kind of editorial, WYSIWYG animation environment. And then we've got Pixar's Presto system underneath showing fur, subdivision surfaces. And fur on a character like that significantly changes the animated performance. So it's very, very useful to see this kind of thing. And then I've also put MPC's example of showing pyroclastic media inside the viewport in Maya. So traditionally you just see a box or some rather crude representation. Now you can work with much more complicated data structures. When it's offline rendering, GPUs have also played a part. This is rather early stuff, using rasterization pipelines and splatting, kind of like the way we used to do it in the old days anyway. Same goes for Sony. Now, obviously that's not the way to use a GPU best. Rendering can only really achieve that level of realism if you turn on ray tracing. And that's been the problem with GPU shaders, anything based on GPU shaders, such as in car designing, modeling systems where you're designing a watch or something like that. If you can't see the refractions and the reflections on those objects, you hit this plateau of realism. Whereas film visual effects, we've relied on ray tracing since the beginning, to a certain extent. If you allow yourself to move to a physically based simulation of rendering, which we're all moving to, and you introduce ray tracing also at the design stage to enable people to see all those interesting light interactions, the whole thing sort of merges together in this area, and you end up with this wonderful sweet spot where you can have GPUs for ray tracing, because they work tremendously well with unbiased ray tracing. And so we've got V-Ray RT, we've got Octane Render, there's NVIDIA's own iRay system, and there are the people that do it kind of like how we used to do it, where it's a traditional rasterizer, but then they tacked on ray tracing as well. And those are situations where optics really comes into play, because optics is one of those drop-in libraries I was talking about. In fact, the people that added it to the Furryville system did it in about 3 months. Similarly, in the studio, Pixar added it into Katana as a viewport plugin. And so they can see the refractions and the complicated shading from their physically based shading models all inside the viewport. Then there's ray tracing at studios. This was really early work that we did called PantaRay, and it enabled them to stream geometry into ray tracing processes to calculate visibility. And the visibility calculations would then be used at a later stage to speed up the final renders. So rigid body simulation is an obvious one too. This was the first time CUDA was used. This was around 2009. Granular simulations, that kind of thing. Resulting in lots of small bits of debris and stuff colliding with each other exceptionally quickly. Fire simulation from fluid it was 2.5-dimensional fluid dynamics. This was done for Harry Potter. You've probably seen the clips from that. That was all done with GPU because this was quite early on, and they hadn't completely gone into a CUDA pipeline yet. After that, they discovered CUDA, and they decided, let's rewrite the whole thing into CUDA, and it didn't take them very long. And they ended up with a system that was far more scalable. We're now starting to see fluid dynamics inside commercial applications as well, obviously. They saw the success of all of this, and they decided, SideFX decided to put it into Houdini 12 as the Pyro system. So this is the roadmap. This is the future, the past and the future of what's happened with GPUs. And what's interesting is you can see all the problems that we've had to overcome. The first problems that I mentioned in 2007 were it's difficult to program. You don't want to have to represent it as a texture map triangle. So we came out with CUDA. The next problem was the precision's not good enough. We want proper floating point. We want double precision, said the supercomputing partners. We went to floating point 64 and improved our 32-bit floating point. And then around 2012, the Kepler architecture introduced dynamic parallelism, which it's very new. But the idea of that is not having to move data back and forth, being able to do as much as possible on a GPU that ordinarily you'd have to pass back. Because the next biggest problem we have to overcome is, of course, the fact that we're on the PCI Express bus. And Maxwell Unified Memory and Volta is stacked DRAM, but I'm going to cover those in a second. All the way through this thing, power is going down. Power requirements are going down. Because, as I said originally at the start of the talk, that is the most important thing, reducing power requirements. This is an example of something we showed at SIGGRAPH this year, which is a 2-watt device running the Kepler chip architecture. So this is the future. This is actually our Logan chip, which is coming out imminently. So when you've got to work with the PCI Express bus, there's a lot of things to think about. This is a huge problem. If we're on the same switch, we're fine. If we're on the same card, we have these Gemini cards with 2 GPUs, we're fine. We can have very, very fast interconnect between the two. But if we have to travel from one socket to another bus, it's a nightmare. And you'll notice this, absolutely, if you put your cards in the wrong configuration. So all these things we have to think about. So we came up with this peer-to-peer API where you now have low-level access to cards that are able to talk to other cards, which is very important for any kind of multi-GPU processing. Because you're going to want to have all these cards doing something and then potentially share data afterwards, move data around. It's also incredibly important when you're doing any kind of streaming that has to be low latency. So with that, we tried to get rid of the bus almost entirely, and we provide cards that let you just jack straight into the GPU, do your processing in CUDA or OpenGL or something like that, and then pipe it straight out again. And this is the stuff that they use in broadcast. This is the stuff that they use in virtual sets and things like that, where you have to have extremely low latency. The next problem is the one that Maxwell's trying to address, which is this idea of GPUs don't have enough memory to do the kinds of things that we in visual effects need to do. And these are just some of the quotes from Transformers 2. I suspect Transformers 3, 4, and 5 probably had way more memory consumption. But what Maxwell does is, instead of thinking of the GPU as 12 gigabytes of device memory, think of it as one really big L1 cache, and we'll just sort of page things, well, L3 cache. It sort of adds another level to the cache hierarchy. We'll page things in and out as we need them across the PCI Express bus, hopefully as efficiently as possible. By that time, we'll all be on Gen 3, and Gen 4 will be down the road. But we do have these big cards. And we have, our biggest card is the K6000, which has 12 gigabytes of RAM. The next generation, we can expect that for the flagship to double. So, and that's looking at a really interesting spot, because once you hit 24 gigs or 32 gigs, suddenly it actually becomes reasonable to consider, well, we could render this entire scene on a 32 gig card, or we do have a big enough domain to work with. But in the interim, the unified memory should do a pretty good job of just reducing performance a touch, but giving you access to a full 128 gigabytes of RAM. And the 12 gigabyte Quadro is, for what ILM is doing with Plume, is exactly that, something that's going to let them do slightly larger, slightly higher fidelity explosions and so forth. The goal, of course, is to be able to render this inside Katana. And finally, there's the stacked DRAM. Now, the stacked DRAM is all about reducing the memory bandwidth, memory latency issue. Because if you have access to all this memory, it still takes a while to access memory. The slowest thing on a computer is always the memory. It's not the computing at all. It's not the maths or anything like that. So the idea of stacked DRAM is it's as close to the chip as possible, because it's also stacked vertically as well. So you reduce the distance, you reduce the latency. It's that simple. And then here's the Tegra roadmap. And the Tegra are our chips that are for the cell phones and the small devices, low wattage devices. The most interesting thing about this is Logan supports CUDA and the latest versions of OpenGL. So all of these things we're talking about, all these ideas, dynamic parallelism, everything like that, is all available also on our low-power chips with integrated memory systems. So that means that all of these capabilities can be done on tiny devices in your pocket, which means ideas like robotics and computer vision with cell phones and Google Glasses absolutely comes into play there. Tracking very complicated environments and reconstructing three-dimensional scenes and so forth is absolutely possible with the next generation of Tegra chips. And then when we reach Parker, we're adding our CPU on as well. And the idea of that then is, of course, we're not dependent on any kind of host device system. We have everything all together. And we can run the very serial operations on the CPU and the very, very parallel operations on the GPU. We also have a conference called GTC, and I'll use this moment to encourage anyone who's interested in GPU technology and meeting a lot of people who work with GPUs but not in games. So all those other areas I'm talking about, oil and gas, computational finance, seismic exploration, astrophysics, all of that stuff, they're all here. So it's rather like this. It's a very small, fabulous little conference where like-minded people can get together and chin-wag about what's best and how great GPUs are. So thank you very much.
I just want to thank all of you who have been supporting us as part of our Insider program. As an Insider member, you allow us to do shows like this, and we try and say thanks by posting bonus exclusive content. So check it out on our homepage at fxguide.com. Well, that's it for now. Until next time, see ya. For more industry news, in-depth features, podcasts and forums, check out fxguide.com. And for visual effects training, check out fxphd.com.